Welcome to our YouTube channel. This is Ernest again, coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that useless hate energy into useful love energy. I mean love for this subject. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. This is our continuing series in Algebra. Specifically, it will be video 3 of the Algebra series. And we'll start off with question D here. If we look at this carefully, we see two terms. We see a polynomial of degree 2, two terms. The middle term is missing. The linear term is missing, and there's a minus sign in between. The objective here is to factor. This is still our section on factoring. It's a continuation from video 2. And so we have two terms. The first thing you should always look for is the GCF. And the GCF for 50 and 72 is 2. So we'll factor out the GCF, put it out front, and use division to find the balance. 50 divided by 2 is 25, so we write down 25x squared. Minus 72 divided by 2 is minus 36, and we're done with the balance. Inside the brackets over here, we identify this as a quadratic, and the coefficients a, b, and c are 25, 0, minus 36. And we could use the EQN3 button on the calculator to actually factor the inside of the brackets. That is to say, to factor the quadratic. That's one way of doing it. And because I haven't mentioned about any other factoring techniques at this point in time, I'm using the EQN3 method. It's the calculator method in order to achieve the factoring. And in the next line, you leave the GCF, you bring the GCF down, and the factors turn out to be 5x minus 6 and 5x plus 6. And that constitutes the factored form. If we look at E, we have 9x squared minus 6x plus 1. We identify that as a trinomial, and it is quadratic. There are three terms, no GCF. 9, negative 6, and 1, no GCF. We identify the quadratic coefficients as 9, minus 6, and 1. Again, we can use the EQN3 button on the calculator. I know you don't understand what that means at this point in time, but take it from me. That calculator button is very useful in terms of factoring, so I'll show you that trick at some point in time. Anyway, the calculator yields 3x minus 1, 3x minus 1. And of course, 3x minus 1 times 3x minus 1 is just a perfect square, and we get 3x minus 1 all squared. And that's the factored form. Again, a similar sort of question. We have a 10a squared plus a minus 3. There are three terms. It's a quadratic in a because the degree is 2. Again, 10, 1, negative 3. There is no GCF. We identify the quadratic coefficients as 10, 1, and negative 3. Again, we can use the EQN3 button. On the calculator, most calculators these days, most scientific calculators do have equation solvers built into them. And they don't have to be graphing calculators, but they have to be fairly recent in order to have that facility in them. But anyway, it would be a quadratic solver that you'd be looking at. I'm not quite sure. It depends on your calculator whether you have an EQN button or not, but most calculators do. So again, through the EQN3 facility, this will factor as 2a minus 1, 5a plus 3, and we declare this to be the factored form. And let's go on to the next slide. Let's look at E. We have a to the power of 4 minus 16, and that gives us two terms, and there's no GCF. And what we're going to use is something called DOS. DOS is short form for difference of squares. If you look at this carefully, there's a difference there. So that's the difference part of difference of squares. This a to the power 4 is actually a perfect square. It can be written as a squared all squared. And 16 is actually a perfect square. It can be written as 4 to the power 2. And that's why this is called a difference of squares. Now, the usual difference of squares factoring formula is a squared minus b squared is equal to bracket a minus b, bracket a plus b. I've thought of a different way of doing this using square roots. It might be a little bit easier for people to understand what to do or to remember what to do. Whenever you see something with the form a minus b, and a is positive and b is positive, we can always rewrite that as square root a minus square root b times square root a plus square root b. Using the fact that root a is just a and root b is just b, we can always expand this to get a minus b again. So this is in fact an identity. That's provided a and b are both positive. And of course, if a is a perfect square and b is a perfect square, the square root of a perfect square is just the inside of the radical. The square root of the perfect square is just the inside. The square root of the perfect square is the number itself. Okay, for example, the square root of 3 squared is 3. The square root of 4 squared would be 4, etc., etc. That's what I meant. But anyway, let's just see how to use this form of difference of squares factoring. Okay, we identify this of the form a minus b, and we're going to do the square root of a here. The square root of a to the power 4, just divide the exponent by 2, you get a squared. And then the square root of 16, you get 4. And then you copy this down twice. You copy a squared 4, and minus plus, and that'll be the factored form for the time being. Now you notice that this is a sum of squares, not a difference of squares, but a sum of squares. And a sum of squares will never, ever factor. Okay, so now we'll look at this term over here, this factor. We notice that this is a difference of squares again. So we can apply this formula again. And we continue. The square root of a squared is a, drop it down. The square root of 4 is 2, drop it down. And then you copy paste, you put an a2 and a2 over here and a minus plus, and that will do the job for the a squared minus 4. So it's the square root of a squared is a, the square root of 4 is 2, copy it down twice, and then do a minus and a plus. Okay, these are called conjugate pairs. Okay, so a difference of squares factors as conjugate pairs. Just remember that little rhyme. A difference of squares always factors as conjugate pairs. And of course, a squared plus 4 is a sum of squares which never factors. Just remember that a sum of squares does not factor. It's only a difference of squares. Okay, let's look at f over here. You have bracket m minus n squared. That's certainly a perfect square, minus 2m plus 3n all squared. And that's certainly a perfect square as well. So we have a difference of two perfect squares. That means, and we have no GCF, so we don't have to worry about GCF. That means we can use our little DOS factoring formula up here. Okay, if you do the if you perform the square root of m minus n squared, you just get m minus m. And the square root of 2m plus 3n squared is just 2m plus 3n. So write it down, write down the m minus m here, and the 2m plus 3m here. And the next set of brackets you clone, you write it down again, and then you put a minus and a plus. Okay, so again, the square root of this is m minus n, put it down. The square root of this is 2m plus 3n, put it down. Then copy paste what you put down, and then you put a minus here and a plus there. And of course the order doesn't matter. You could have put a plus here and the minus there is irrelevant. I usually like putting the minus here and the minus sign up front and the plus sign over here for calculus reasons, okay? Because you use difference squares a lot in calculus, it makes your life a little bit easier if you dot the a minus b, a plus b convention instead of a plus b, a minus b convention. Okay, so now at this point in time, all you have to do is remove the inside brackets, And when you do that, you get an m minus n here. You distribute the minus sign, you get minus 2m minus 3n. And over here, you remove the brackets, you get m minus n, and you get 2m plus 3n. And then inside each square bracket, you collect like terms. You have m minus 2m is minus m, and minus n minus 3n is minus 4n, and m plus 2m is 3m, and then minus n plus 3n is plus 2n. Over here, you'll notice you can factor out a GCF of negative 1, or equivalently, you can factor out a minus sign, and that's what I did in the next step. When you factor out a minus sign, and of course you can replace the square brackets by round brackets because we're all done, you get a minus bracket m plus 4n, bracket 3m plus 2n, and that's the factored form. Okay, so you need a little bit of practice using this difference of squares formula up here in order to obtain the factored form. Okay, let's go on to the next slide. And this first question over here, question 9a, is the beginning of the section dealing with rational expressions. A rational expression is a fractional expression. And up to this point in time, we haven't really talked about restrictions, but we need to talk about restrictions at some point in time, and this is a good time to talk about it. Okay, so let's look at what we have, and we'll get down to the restrictions after. Question 9a. We have a quotient, and a quotient is also called rational. We have 10a squared dot b plus 15b dot c squared all over minus 5b. The idea here to reduce this is to divide term by term. When we have 10 divided by minus 5, you get minus 2. And then a squared dot b divided by b will just give you an a squared. Okay, actually I showed it very like in little baby steps. Okay, let's do it again. You get 10 divided by minus 5 will give you minus 2. And then a squared is alone. And then you get b to the power 1 minus 1. Because you get power 1 up here and minus 1 down there. So you get b to the power 1 minus 1. And then we get 15 divided by negative 5 is minus 3. And then we get b to the power 1 minus 1. And then we just get a c squared. And notice that b to the power 1 minus 1 is just b to the power 0, which is 1, so it drops out. But still, even though it drops out, we've got to be very careful in terms of restrictions. So we wind up getting a minus 2a squared minus 3c squared. I declare this to be the reduced form of the original problem, except that's not really the end of the story. That's the end in terms of the simplified form, okay, but it's not quite the end of the story until you impose restrictions. If you go to your calculator at this point and punch in 0 divided by 0, for certain you will get a math error. And if you go to your calculator again and try 1 divided by 0, again you will get a math error. Whenever you divide 0 by 0, okay, that means you have a cancellation going on. When you divide 1 by 0, that means that you have a vertical asymptote going on. Okay? So 0 divided by 0 will actually yield a whole, what is called a whole. More will be said about wholes and vertical asymptotes in another video. But what you really need to remember now is that 0 over 0 is called an indeterminate form, and it will yield a whole. If you were to plot a graph, it'll yield a hole in the graph. And 1 over 0 will actually yield a vertical asymptote if you were to plot a graph of the expression. But that's as far as I want to take it right now because it gets quite involved. All you need to know at this point in time is that the calculator will definitely hiccup when you punch in 0 over 0. and it will really hiccup when you punch in 1 divided by 0. Okay, for 0 over 0, it's just a hole in the graph, and a hole in the graph is like a pothole in the road. And for digging up a pothole in the road, all you can do is get some jail time. Okay, and potholes in the road come from cancellation, so that's why I write down CAN. Now, 1 divided by 0 is not a pothole in the road. It's actually a fault in the road. Okay, it's like a sinkhole. It's like part of the road just caves in. Okay, it's like over here in Ontario, we have the Niagara Escarpment. It would be like the Niagara Escarpment. Okay, you don't want to go off a cliff. Okay, so 1 over 0 is like going off a cliff with your car, and 0 over 0 is just a pothole in the road. A pothole in the road is manageable. The most you can do is damage your car a little bit. You can always repair the wheels. You can repair the front end. But when you go over a cliff, it's game over. Okay? So when you commit this kind of an error, 0 over 0, think about it as going to jail. When you commit this kind of error over here, think about death penalty. Okay? So you wind up getting the death penalty here and just going to jail over here. Okay, by the way, we don't have the death penalty over here in Canada, but, this is just a figure of speech, okay? Don't take it to be any more than that. That's just to realize that 0 over 0 is severe, but not so severe. You just go to jail. And 1 over 0 is very severe, and, there are consequences involved, okay? Now, in this case over here, we have to be able to identify the cancellations. The cancellations came about by B over B. Of course, the B's canceled. How do we recognize a cancellation using exponent laws? When you see a minus sign, okay, you see the 1 minus 1? The minus sign indicates that there's been a cancellation. The minus sign indicates a cancellation. At the end over here, you notice at the end over here, there's no possibility that the denominator can be 0, because the implied denominator over here is really 1, and 1 can never be equal to 0. So nobody dies over here. There are no restrictions. There are no 1 over 0 restrictions. The only type of restriction is a jail restriction of the form 0 over 0. Okay? So this corresponds to a hole in the graph, and all you get is jail time. If you violate this restriction, the restriction is that B cannot be equal to 0. Because if B were equal to 0, you'd be canceling out 0 over 0 here, and you'd be canceling out 0 over 0 here. Not allowed. So in violation of this, you go to jail. But of course, we're not going to violate it, so we're going to state that B is not equal to 0. So this is a restriction which allows you not to go to jail. Okay, so the restriction makes sure that you don't go to jail, and it makes sure that you don't die. Okay, so be sure to indicate the restrictions so nobody gets killed here. Otherwise, if you don't state restrictions, the original expression is not identical to the reduced form down here. Okay, so the sermon is over. I'm going to go on to the next slide. We'll do another question that's very similar to that. You recognize this as a quotient. You have a big numerator on top and a monomial denominator on the bottom. And again, to reduce this, I'm going to divide term by term. You do 30 divided by 10 will give you 3. X squared over x squared will give you x to the power of 2 minus 2. And y cubed is just y cubed. And then minus 20 divided by 10 will give you a negative 2. X squared over x squared will give you x to the power of 2 minus 2. And then we have a remaining z squared. 50 divided by 10 will give you 5. X squared over x squared will give you x to the power of 2 minus 2. And again, x to the power of 2 minus 2 is x to the power of 0, which is 1. And that is true if and only if x is not equal to 0. That's the key. That's the key. 0 to the power of 0 is undefined. It is not equal to 1. So the only way we can insert a 1 for x to the power of 0 is if x is not equal to 0. Okay? Every other value of x will give you, like 2 to the power of 0 is 1, 10 to the power of 0 is 1, negative 2 to the power of 0 is 1, except for for 0 to the power of 0. If you try that on your calculator, you will get a math error. Okay? So at the end, you can drop the 1. So the reduced form, so this just becomes a 1. The reduced form becomes 3y cubed minus 2z squared plus 5. That's the end of the problem. Okay? So for the 0 over 0 restrictions, or for the cancellation restrictions, we look for cancellations. Okay, where did we do a cancellation? Over here, when you have a minus 2, you're really canceling. So that means that x cannot be 0. When you're performing the minus 2 over here, you're really canceling. So x cannot be 0. When you have the minus 2 here, you're really canceling. So x cannot be 0. Okay? So that's the only cancellation restriction. X cannot be 0. At the end, the implied denominator over here is 1. And 1 can certainly never be equal to 0. Therefore, nobody dies. There is no 1 over 0 restriction. Okay, so the only restriction to recap is that x cannot be equal to 0. So we'll continue. Again, the same sort of problem, so we'll have another shot at it. We have a big quotient on top, a monomial denominator. Okay, trinomial numerator, monomial denominator. So we're going to divide term by term. We get 16 divided by 8 is 2. M divided by m will give you m to the power 1 minus 1. N divided by n will give you n to the power 1 minus 1. And r is just a drop down. Minus 24 divided by 8 will give you negative 3. M divided by m will give you m to the power 1 minus 1. N divided by n will give you n to the power 1 minus 1. And p is just a drop down. 40 divided by 8 will give you 5. K is just a drop down. There it is right there. M divided by m will give you m to the power 1 minus 1. And n divided by n will give you n to the power 1 minus 1. Recall that m to the power 0 is 1 if and only if m is not equal to 0. N to the power 0 is 1 if and only if n is not equal to 0. And the same holds true over here. So we have a cancellation restriction. And at the end, we get over here 2r minus 3p and then plus 5k. And that's the reduced form. And now we must impose restrictions. Otherwise, the original expression is not equivalent to the reduced expression. Not. Okay? Because over here, there appear to be no restrictions. But over here, there certainly are restrictions. So this is almost equivalent to that, but not quite. It will be perfectly equivalent to that, provided you provide restrictions at the end. That's why the restrictions are absolutely necessary to ensure that a large expression that you start off with is indeed equivalent to the reduced expression. So this end expression, together with the restrictions, will ensure that this is equivalent to this and that. Okay? So the restrictions are m cannot be equal to 0, n cannot be equal to 0. The implied denominator over here is 1, which certainly cannot be equal to 0. So there are no 1 over 0 restrictions. Okay? So there we have two whole restrictions and no vertical asymptote restrictions. Okay? So two whole restrictions, because jail means you have a hole, and die means you have a vertical asymptote, which is like a cliff. Okay, so that's the end of that problem. Let's go on to the next slide. And I think we'll do an over and out for this video and continue in another video. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Math Lab Tutorials in Toronto.